we expect the James Webb Space Telescope, JWST, to make significant disclosures. We anticipate that just minutes prior, the JWST found something uncommon that is shaking the very underpinnings of our understanding of the infinite. This revelation is modifying the guidelines of our universe as we know it, as researchers update their hypotheses from finding hidden astronomical secrets to uncovering universes beyond imagination. The JWST's most recent disclosure has set established researchers burning with expectation. With every observation, this cutting-edge telescope takes us back in time, disclosing mysteries about the beginning of the universe. What could be the nature of the enormous object the JWST recently distinguished? How might this latest disclosure change our impression of the universe and its secrets? December 25, 2021, marked a giant leap for mankind in space exploration. On this portentous day, the James Webb Space Telescope was launched as the most refined instrument for infrared cosmology and space science. Its advanced capabilities allow for the investigation of the farthest and earliest stars and galaxies in the universe. With its exceptional resolution and sensitivity, the JWST has presented to us a new dimension of invaluable perception. One of the major forward leaps of the JWST is its ability to outstandingly explore the past, providing us with a brief look at the first stars and the development of early galaxies. It helps researchers make accurate analyses of the atmospheres of habitable exoplanets, as well as the puzzling features of black holes dispersed across the universe. Black holes are mysterious cosmic objects formed by the remnants of collapsing stars. They exert gravitational forces so intense that even light cannot escape their pull. Black holes are regions of the universe where reality is distorted by an event horizon. The event horizon is called the final frontier, a region that challenges the principles of modern physics. While black holes are relatively new discoveries, the theory of relativity had hinted at their existence long before they were finally confirmed. The theory proposes that sufficiently dense masses can warp spacetime to create the unusual structures we call black holes. Initially undetectable, the reality of black holes is uncovered by their gravitational influence on surrounding material. Space telescopes, prominently the JWST, utilize various advanced instruments to identify the unmistakable signs of a black hole's presence. Researchers can deduce a black hole's properties by observing how nearby stars and gas behave around these objects. Specifically, they investigate the gravitational effects on adjacent stars, determining whether they orbit or are pulled away by the immense gravitational pull. Generally, the James Webb Space Telescope, equipped with cutting-edge instruments and extraordinary features, helps us look deeper into the universe to solve problems that were once thought to be unsolvable. As a black hole and a star draw near, they emit a lot of high energy, and the cosmic scene becomes extremely bright. However, despite their dramatic effects on surrounding matter, black holes possess an unusual property: their internal structure remains elusive, as governed by the theory of relativity. This is because the gravity of the black hole dictates the fate of any object that dares to venture too close. The no-hair theorem further explains the mystery of black holes. It suggests that once a black hole achieves stability following its formation, it has only three measurable properties: mass, electric charge, and angular momentum. However, this simplicity conceals the complexity of these cosmic entities, making it challenging to distinguish black holes even if they share the same physical characteristics. By examining the types of black holes we observe, we see that they are a diverse family, presenting distinct features. The first type is the stellar mass black hole, which is the smallest, having a mass between 1 and a few times that of the Sun. At the far end, we have supermassive black holes, weighing millions or even billions of times the mass of the Sun. According to scientific theories, the death of massive stars in the early universe gave rise to these truly massive black holes with masses exceeding 1,000 suns. In the intermediate position, we find intermediate black holes, which fall between their stellar and supermassive cousins. Interestingly, contrary to popular belief, some black holes are relatively small, appearing almost as tiny as a molecule. Yes, it seems difficult to imagine or believe that massive stars can have such a minute size and yet maintain such a huge mass, much greater than that of an entire mountain. Nevertheless, this is the reality of the cosmos. Investigating the Milky Way, we find countless black holes spread across the universe, each with masses equivalent to millions of solar masses. Hypothetical observations and experience have shown that large black holes tend to occupy a central position in galaxies, including our Milky Way. At the core of the Milky Way lies Sagittarius A*, a supermassive black hole with a staggering mass comparable to around 4 million suns. This makes it the largest object in its surroundings. With increasing research on black holes, what makes these entities so intriguing is their complexity, which has kept researchers engaged for decades. These enigmatic structures are laboratories for examining numerous well-established theories, including relativity, quantum mechanics, and cosmology. They have driven physicists into uncharted territories of physics, putting our current understanding of the principles of the universe through a rigorous reality check. However, our knowledge of black holes continues to be refined with the advancement of newer observational methods and technological progress. Yet, our understanding of black holes remains limited, as we cannot directly observe them. Stellar mass black holes reach temperatures in the billions of Kelvin, and investigations are confined to indirect methods and theoretical frameworks. At the heart of the intriguing nature of black holes lies the event horizon, a boundary in spacetime from which no information, not even light, can escape. This characteristic of black holes is more than just a simple gravitationally strong object, it is a realm of reality beyond human comprehension. As we approach the event horizon, the laws of physics undergo a significant shift, offering only a glimpse into the secrets of these entities. What we know for certain is how some of these black holes are formed. It is an established fact that the gravitational collapse of stars often leads to the creation of black holes. This typically occurs when an object's internal pressure fails to resist its own gravity. Researchers emphasize the importance of high-density conditions for this collapse in the current epoch of the universe. Such densities essentially exist within stars. Anyway, during the early post-enormous detonation, universe densities were essentially higher, likely contributing to the creation of dark openings. The separation of high-density dark openings also requires the mass to be unevenly distributed to prevent it from becoming uniform. For early-stage dark openings to form in such thick conditions, there must have been initial variances in density, which allowed them to grow through gravity. However, gravitational breakdown isn't the only way dark openings are shaped. High-energy crashes can also create dark openings, provided they achieve sufficient density. Since 2002, no such events have been identified directly or indirectly demonstrated by mass imbalances in atom smasher analyses. Of all that is interesting about dark openings, the most captivating is their dynamic nature. They do not have distinct sizes and can continue growing unbounded by consuming the surrounding matter. Every dark opening survives by ingesting gas and dust found in space, ultimately leading to their remarkable growth. This ability is one of the key features responsible for the formation of some truly massive dark openings. Furthermore, dark openings can merge with other objects, like stars or even other dark openings, to form a colossal dark opening. To this day, dark opening development remains a topic of study, and with the activity of the James Webb Space Telescope, JWST, we are set to uncover more in-depth details. There have been concerns about the possibility of a dark opening stirring things up and destroying our planet. However, thanks to diligent researchers, these worries have been laid to rest. They have demonstrated that this scenario cannot occur. In fact, if we were to somehow replace the Sun with a dark opening of the same mass, the Earth would not be sucked into the event horizon, rather, it would orbit the dark opening just as it orbits the Sun, due to the identical gravitational force. Additionally, dark openings do not move through space consuming celestial bodies like stars, planets, or moons. Therefore, Earth, as a planet, would not succumb to a dark opening, as none are currently in proximity to our solar system. In conclusion, the Sun cannot evolve into a dark opening, as it lacks the necessary mass to collapse. Returning to the James Webb Telescope, this exceptional equipment is not only powerful enough to observe nearby celestial objects, but it also identifies elements from the distant past. the most recent success is the discovery of around 400 objects in the near vicinity of our solar system that were previously unknown. This discovery has sent a wave of excitement through the scientific community, highlighting the telescope's significant impact on our understanding of the universe. It is fundamental to remember that Earth, stars, and galaxies are dispersed in space, filling roughly 5% of the universe. This fact strongly suggests that there are numerous other possibilities within our universe that we are not yet aware of. The JWST is a key impetus for breaking ideal models and unlocking secrets, one mystery at a time. The JWST serves as a gateway to a new phase in space research, allowing us to explore the cosmic secrets that lie beyond the realm of our imagination. It has not only discovered many strange objects in the dark and unfamiliar 95% of our universe but has also revealed the mysteries of our reality. Countless scenarios have transpired in the vastness of time, yet they remain hidden in the depths of the dark universe. Thus, uncovering these mysteries is essential to understanding our universe and its fundamental laws. The JWST acts as a time machine, enabling us to trace back to the universe from the very first light to the formation of galaxies over time. As research continues, a staggering discovery has transformed our cosmic perspective. The telescope revealed many ancient galaxies dating back as soon as 600 million years after the Big Bang. This momentous discovery owes much to the James Webb Space Telescope's Advanced Deep Extragalactic Survey Program, affectionately known as JES. The JES project provides the vital data for the early era of star and galaxy formation, combined with modern technology. The JWST continues to shape the way we think about and describe the vastness of the universe, revealing the secrets locked within reality through the space telescope. Researchers spent long hours achieving meticulous work that included disentangling, examining, and cataloging faint distant galaxies. One of the central figures in this work was Ryan Enney, a student from the University of Texas at Austin. The primary focus of his research is galaxies that existed at the dawn of the universe, around 500 to 800 million years after the Big Bang. Researchers call this period the epoch of reionization. From the studies conducted by Enney and many other researchers, it is evident that immediately following the Big Bang, the universe was enveloped in a fog of gas, rendering it opaque to energetic light for many years. Around 1 billion years post-Big Bang, this fog dispersed, revealing cosmic transparency, or reionization. This event is theorized to have been aided by dynamic, very massive dark openings or galaxies filled with hot, energetic stars. The JES program assisted Enney and his colleagues in analyzing these galaxies using the JWST's near-infrared spectrograph instrument. Their efforts were focused on identifying signatures of star formation, a pursuit that yielded astonishing results. Surprisingly, nearly every galaxy they studied exhibited bizarrely vigorous emission line signatures, indicating recent star formation. Enney contends that cosmic explosions from the very massive early stars were the primary sources of the heat. Furthermore, the data collected showed that star formation in these young galaxies displayed a pattern of long periods of intense star formation, followed by brief intervals of ionization when the activity of star birth declined significantly. This phenomenon is likely because massive stars exhaust their fuel quickly, resulting in supernova events, which could have poured energy into their surroundings, thereby obscuring conditions necessary for gas to accumulate to form new stars during such calm periods. Delving further into the narrative of the universe's formation, JES plays a crucial role by casting a net to capture the early galaxies that existed less than 400 million years after the Big Bang, even when the universe was still an incredibly young entity. The high-level principles of this study are vital to unraveling the mysteries of how stars formed in the initial thousands of years after the Big Bang. Although these galaxies are many light-years away, the light coming from them is altered and undergoes changes throughout its journey. Cosmic excursion in the growing universe. By and large, the development of the universe extends the light to longer frequencies that seem redder in color, a peculiarity named redshift. Stargazers utilize this redshift to judge the distance of systems, and the same impact can assist with recognizing those worlds that formed at the early stages of the universe. Before the advent of the JWST, our perceptions were limited to a mere few dozen galaxies with a redshift exceeding 8. A redshift of 8 corresponds to a time when the universe was younger than 650 million years old. Anyway, the JWST program has reformed our capabilities, enabling the detection of almost 1,000 of these truly distant worlds. When researchers try to describe a cosmic system, traditional techniques include analyzing its brightness across numerous tightly spaced frequencies. However, an alternative methodology involves capturing images of the galaxy through filters that specifically detach tight bands of colors. This technique yields a small handful of brightness measurements while working with the assessment of distances for large numbers of galaxies. The beauty of this methodology lies in its efficiency, which empowers scientists to gain valuable insights into the universe through the combined efforts of projects like JWST and cutting-edge technologies. The secrets of space are increasingly being unraveled, offering an exceptional glimpse into the early time of our universe's evolution. Meanwhile, Eni wasn't the sole academic engaged in the project. Kevin Hainline from the University of Arizona, Tucson, also used a near-infrared spectrograph instrument to capture measurements. These measurements, termed photometric redshifts, proved instrumental in identifying over 700 galaxies that flourished when the universe was between 300 and 650 million years old. This is a new discovery that resonated throughout the global academic community, as the sheer abundance of these galaxies far surpassed previous forecasts, shaking the foundations of past perceptions. Before the launch of JWST, cosmologists had very little understanding of the evolution of these distant galaxies. However, JWST has broken limits, offering entirely new perspectives previously unexposed by the Hubble telescope. Besides the discovery of new celestial objects and cosmic wonders, the telescope has also been utilized to find exoplanets and celestial bodies that might harbor signs of life. The ensemble for the study of extraterrestrial life reverberates amidst the universe of researchers. The James Webb Space Telescope has thrown a steady stream of dazzling pictures into the public domain since its launch. It has provided an extraordinary glimpse into the atmospheric conditions of foreign celestial bodies while investigating new mysteries hidden within the Milky Way and beyond. Among these revelations is the exhilarating possibility of life on Proxima Centauri b, also known as Alpha Centauri b, which may be the site of Earth's first extrasolar state. This mysterious discovery is the type of hypothesis that ignites the imagination, and this exciting event represents the motivation behind JWST. Proxima Centauri b, an exoplanet settled within the habitable zone of its red dwarf host star, Proxima Centauri, holds much significance in the scientific community. Proxima Centauri is the closest star to our Sun and is part of the vast Alpha Centauri triple star system, situated remarkably close to our solar system. Proxima Centauri b has garnered attention as a potential Earth-like world. This exoplanet completes its orbit around its parent star at a distance of roughly 7.5 million kilometers, with an orbital period spanning approximately 11.2 Earth days. Its mass surpasses that of Earth by at least 1.07 times and has a slightly larger radius. Proxima Centauri b presents fascinating parallels to our own planet. Nonetheless, the JWST discovery of its placement within the habitable zone leaves confirmation of its atmosphere elusive. This uncertainty stems from Proxima Centauri's nature as a flare star, emitting intense electromagnetic radiation capable of stripping away planetary atmospheres. The quest to resolve this uncertainty continues, with hopes pinned on future observations. Proxima Centauri b is an intriguing exoplanet, much closer to its star than Earth is to the Sun. However, we do not yet know its age, which is crucial for understanding its history. Researchers are using computer simulations to learn about how Proxima Centauri b formed. Their investigations have revealed much about Proxima Centauri b, including how heat is generated within the planet and how it rotates. Despite being similar to Earth, it likely formed under different conditions, with less water and more intense impact events. Plans are currently underway to send probes to explore Proxima Centauri b through projects like Breakthrough Starshot. These efforts could help us find signs of life on this captivating exoplanet. As we continue to explore and make new discoveries, Proxima Centauri b presents exciting opportunities for finding extraterrestrial life. We can hardly wait to see what researchers uncover in the future.